Included on your quiz tomorrow. So the quiz tomorrow includes 2-2, which is your graphing packets. Make sure you can factor to find zeros, identify multiplicities, do your end behavior and write it in the mathematical notations. You could find a y-intercept and put all those things on a graph together. 2-3, make sure you feel comfortable with synthetic and long division. You don't know which one you'll need to be able to do. And things like verify factors. So make sure that your remainder is equal to 0. And then this section is also on the quiz tomorrow, so complex numbers. But I would say most of us are probably going to feel pretty comfortable with this. So first things first, we're going to just talk real quick about complex numbers. Complex numbers have what we call standard form. And mathematicians all agree to write complex numbers in the same standard form. So everybody here in room A08 who are mathematicians, that's all of you, will also be writing in the standard form a plus bi. And, think about a plus bi. A is your real part, and bi is your imaginary part. So when you're writing in standard form, always make sure the imaginary part is at the end. The real part comes first. So the i's are always at the end in standard form. You were introduced to last year, and it's called the imaginary unit. Does anybody remember, what do we equate I with? What value, Dylan? Square root of -1. So you probably had some discussions back then about the fact that you can't really take the square root of -1. There is no number that multiplies by itself to give you a negative. But mathematicians needed a placeholder. Well, let's imagine we could take the square root of -1. Let's just call it I. So that's what we did. That is what opens us up to the complex numbers. So just to kind of make sense of the complex number system, know that before you were introduced to i's, you only knew about real numbers. That was your big box of numbers. And your big box of numbers could always be split irrational or rational. And then you could break up the rational numbers. You could say integers, there was a subset whole numbers, there was a subset natural numbers, there's a subset. So you could break those up. When you were introduced to the imaginary unit, that opened up your box. You have a bigger box of numbers now. So complex numbers is everything. Real numbers is a subset of the complex numbers, and imaginary numbers are also a subset. So real numbers are actually complex numbers in the form a plus 0i. So our counting numbers 1, 2, 3, they're actually complex. 1 plus 0i, 2 plus 0i, 3 plus 0i. We just don't teach them like that in the beginning. Okay? And then imaginary numbers are any numbers in the form complex numbers a plus bi such that b is not equal to 0. So if b is not equal to 0, you have an imaginary part, which makes it imaginary. Now, just like there are subsets of real numbers, there's also a subset of imaginary numbers. This is not something that I'm ever going to ask you about, but I always like to mention it. A subset of imaginary numbers are called pure imaginary numbers, and pure imaginary numbers have no real parts. So they are of the form 0 plus bi. So if you ever do the square root of -4 and you get 2i, that's a pure imaginary number because it has no real part. If it's 3 plus 2i, it's just an imaginary number in the subset of complex. Okay, so jury's still out based on talking to my previous 2 classes whether or not you talked about cycles of I in Algebra 2. I'm not convinced one way or another. I thought maybe you did, but I'm not sure. So we're going to look at the cycles of I next. Okay, so the cycles of I are dealing with the exponents. If you take I and you raise it to different exponents, what we find out is it starts to repeat itself. So it has a cycle that it runs through. So let's just think back to exponent properties. If you take I and raise it to the 0 exponent, then it equals 1. Anything raised to the 0 0 is equal to 1, even the imaginary unit. So I equals 0 is 1. Okay, now I to the first is really just I, which is the square root of negative 1, but we don't write square root of negative 1, we all write I. So I to the first is just I. We like to write it as I instead of the square root of negative 1 so that if I were just left out some math work and Anna happened to come across it, if she saw the I, she would immediately know it was imaginary, as opposed to square root of negative 1 doesn't like stand out as imaginary to everybody. Okay, but the I would be like, hey, this is imaginary. Okay, I squared is basically, I'm going to show my work over here on the side, I times I, which is the square root of negative 1 times the square root of negative 1, so that should give us negative 1. If you take the square root of 2 times the square root of 2, you get 2. So it's like the square, or I square root of negative 1 squared. So we're going to get negative 1. And then when we get to I cubed, you could think about I cubed. I like to think about it like I squared times I. Well, I squared is really negative 1. Negative 1 times I is just negative I. Now, if I did another one, so I'm going to do I to the 4th. I know I'm getting low on the bottom of the screen here, but I'm going to do I to the 4th down there. There's a couple different ways you could see I to the 4th. You could see I to the 4th as I cubed times I, but we could also write it as I squared times I squared. Well, if I took I squared times I squared, that would be negative 1 times negative 1, which would be 1. And notice that's the same as I to the 0. So then if I do I to the 5th, it's going to be I to the 1st, I to the 6th, I to the 7th. So I'm going to highlight my cycles of I. It's got a lot of stuff up there. You have 4 cycles. I to the 0, I to the 1st, I cubed, I to the 4th. And then you repeat. So I to the 4th, I to the 5th, I to the 6th, I to the 7th, I to the 8th, I to the 9th, 10th, 11th, 12th, oh my gosh, 13, 14, 15. Okay, cool. Okay, so it's just going to keep going round and round and round, right? Okay. Now, sometimes we'll get problems like this, and you're going to do some operations with complex numbers here in just a little bit. And if it's not in standard form, a plus bi, you would use the cycles of I to simplify it. So if I have something like 2I cubed plus I squared, I have to think about the cycles of I. I cubed is really negative I, so I'm going to show my work here. 2 times negative I plus I squared, which is really negative 1. And then make sure it's in standard form, real part first, imaginary part second. That number in standard form is actually negative 1 minus 2I. And you should write it like that, not like 2I cubed plus I squared. But then there are some other problems where you might want to do 5I to the 25th plus 3I to the 74th. And I'm thinking, I don't really want to have to figure out all the way to 25 or 74 what the cycle of I is. Go around and around and around. So we're going to look for patterns in that cycle of I to help us. Okay. Let's look, and we're focused on the exponents. Let's look at exponents for I to the 0, which is equal to 1. If it's equal to 1, it's things like I to the 4th, I to the 8th, I to the 12th, I to the 16th, 20th, 24, 28, 32. What do you notice about all those numbers? They're all multiples of 4. And if you take a multiple of 4 and you divide it by 4, what is always true in the division algorithm? The remainder is 0. Divided by 4, the remainder is 0 every single time, right? 32 divided by 4 is So if you can divide your exponent by 4 and its remainder is 0, then it is I to the 0. Now, let's take a peek at the exponents for I to the first, which is equal to I. We've got 5, 9, 13. If you take all of those numbers and divide them by 4, what is always true? 5 divided by 4, 9 divided by 4, 13 divided by 4. Remainder is 1. Okay? So if the remainder when you divide by 4 is 1, then it's I to the first. Okay? So the exponent in the cycle of I is going to match the remainder. So the next set, let's just kind of verify that this works out. 6, 10, 14. If I divide those by 4, then my remainder is 2 every time, and it's I squared. So the next ones are going to be remainder 3. Later in math, if you keep going, you learn about something called modular systems. And modular systems work off of this cycle of a remainder. Okay? So when you get back to 0, you start over, and you just keep repeating. All right, so we're going to do 5i to the 25th plus 3i to the 74th. For 5i to the 25th, I'm going to think about 25 divided by 4. What would be my remainder? 4. Wait, 1?
Yeah.
I thought someone said 4. I must have been just dreaming. Remainder 1. Okay, 5i to the first. 25 divided by 4 is 6, remainder 1. All right? Then I've got plus 3 times I to the 74th. If I divide 74 by 4, what's my remainder? 2. Okay? And if you can't do it in your head, you just write it off to the side. It'll be like a nice little trip down memory lane. Division is so fun. Okay, so you get 34, and then, okay, 8. Oh, yeah, it's going to be remainder 2. So this is I squared. And then we're kind of back up to this piece here. We still got to get it in standard form. So make the substitution with the cycle of I. I to the first is really I. I squared is really negative 1. So this is going to be negative 3 plus 5i. Okay? Questions, concerns? So nice use of patterns there on your remainders. You can do higher exponents. If I give you I to the 2,579, I don't expect you to run through that many cycles of I. Okay, just divide. Okay, next up. You have some examples that you're going to run through for me. So we're going to practice operations of complex numbers. You're going to do the easy stuff on your own. Then we're going to come together in the last 10 minutes of class and do the division together, because that's the one that people usually have trouble with. So notice on this side of the room, back by Anna, I've got A, and then it goes B, C, D, E, so there's 5 problems. And then on that side of the room over there by Case, I've got A, B, C, D, E on white paper. Okay. So you want to try to get those 5 problems done before, what time do we got, 35? Yeah. So I'm going to give you about 7 minutes to do 5 problems. You might want to get out of your seat if you can't see to write them down. If your group doesn't know what to do, there are a couple hints at the top of each paper. And then the answers are on the back. So after you do one, flip it up, check your answer. Okay. So do as many of you can in the next 7 minutes. If you need to get out of your seat and see something, do it. And you can talk to your group members and share out answers.
the same. What'd you get? What'd you get? Five.
Okay, it's about 11:25, and I want to make sure we can do a division and answer any questions or clarifications on division. So if you didn't get all 5 done, that's okay. If you want to jot them down and their answers before you leave today, that's fine. Also, on my PDF notes that I'll post online, I'll put the problem and the answer so that if you want to try some of the other ones just to make sure you're doing them correctly, you can. You can also do the homework assignment and check your odds in the back of the book. Basically, just a couple of quick things I would say about adding, subtracting, and multiplying complex numbers. In math, it doesn't matter what grade level or what class you're taking, addition and subtraction is always the same concept, combine like terms. So in this case, we can combine real parts with other real parts and an imaginary part with another imaginary part. I do usually make a note to myself that if I'm subtracting, I have to remember to distribute that negative. So subtract all of the next complex number. For multiplication, I think instantly a lot of people just go right into distribution, or some of us, if it's a binomial times a binomial, may call it FOILing. So you're just distributing. The one thing to remember about multiplication is here's where you're going to use your cycles of I to get it back to standard form. So if you multiply an I by an I and get I squared, you have to change that to -1. Okay, I shouldn't see I squareds or I cubes or any other I's in your answer but A plus BI. So those are just a quick couple things to remember. Now, before we do our example for division, I want to talk about something called complex conjugates because we use them when dividing complex numbers. So I've actually mentioned the phrase conjugates a few times this week. When we were doing that problem on the blue graphing exploration, letter C together, and we had 2 irrational solutions, 1 plus the square root of 3 and 1 minus the square root of 3. Irrational and imaginary solutions always come in pairs, and they always come in conjugate pairs. So 1 plus or minus the square root of 3 is an example of a conjugate. It's the same 2 terms with the different sign in between them. And then when we wanted to multiply that out into a standard form polynomial, we distributed the negative through in the x minus k factor, and I regrouped it into a new binomial. I had x minus 1 as my first term, and then my second term in both parentheses was a square root of 3. And the only difference between the 2 set was 1 was plus square root of 3 and 1 was minus square root of 3. So I said that was really like taking a plus b times a minus b. Well, a plus b and a minus b are another set of conjugates, a plus or minus b. So we have something called complex conjugates, a plus or minus bi. And we're going to use them when we're dividing for a very special reason, because something special happens in real numbers and in complex numbers when you multiply conjugates together. So I'm on this slide going to show my multiplication for the conjugates. A plus bi times a minus bi, because I'm not putting numbers in, I know it works for any set of complex conjugates. Distribute, I'll get a squared minus abi plus abi, and then for those last terms it's going to be minus b squared I squared. Positive bi times negative bi. Now, what's the great thing about multiplying conjugates? Middle terms cancel out, which is why that was so great when we did that writing of the polynomial. We didn't have to worry about all those square roots. Now, in the complex conjugates, I'm going to do a little simplifying here. A squared minus b squared times I squared, but I squared is really negative 1, so that's a squared plus b squared. So when you multiply two complex conjugates together, it's always a squared plus b squared, no matter what your a and your b are. And if it's a real number conjugate, like a plus b times a minus b, it doesn't have the I to change the sign, so it always comes out to a squared minus b squared, which is what I did on letter C on the blue packet. I use this as a shortcut. So I don't FOIL out conjugates, I just do a squared plus b squared if they're complex. And what's so great about this is a squared plus b squared doesn't have an I in it, so that's a real number every single time. You multiply two complex conjugates, you get a real number. And that leads us to dividing complex numbers. So I've got one example that we'll run through together. Note that when dividing complex numbers, you're not really dividing. Okay. It's more of like a simplifying sort of thing. So there's an old rule in math that says you can't leave square roots in the denominator, so you just have to rationalize your denominator. Well, we extend that into the complex numbers. Since I is the square root of -1, we don't want to leave I in the denominator either. So when I look at this, I see 2 plus 3i over 4 minus 2i, I'm not allowed to have I in the denominator. So then I got to come up with a plan. How am I going to get I out of the denominator? We're going to use what we just saw on the last slide. If you multiply two complex conjugates together, you get a real number. So whatever's in your denominator, multiply by the conjugate. So this says 4 minus 2i, then I multiply by 4 plus 2i. Multiply by complex conjugate. If you don't know what a conjugate is and you're writing this in your notes, you better write switch signs. So when you look at your notes, you know what you mean to do. I get a lot of people who are going to multiply 4 minus 2i by 4 minus 2i. I hate to report, but your i's will not cancel. And I get some people who multiply by complex conjugate of the denominator. Okay. Now, if you multiply the denominator of a fraction by 4 plus 2i, then you got to multiply the top of the fraction by 4 plus 2i, so that way you're really multiplying by 4 plus 2i over 4 plus 2i, which is 1. So you're changing the way it looks, but you're not changing what it is. And then that really just makes a division problem two multiplication problems in one. In the numerator, you've usually just got to distribute. So I'm going to FOIL that out. 8 plus 4i plus 12i plus 6i squared. And then I'm going to go in later and clean up all the terms. In the denominator, if you want to FOIL it all out, that's cool. What do you know is going to happen? The outside and inside terms are going to cancel. And I also know from my previous slide that if I'm multiplying two complex conjugates, it's just going to be a squared plus b squared. So I'm going to do 4 squared plus 2 squared. It doesn't matter if it's 2 or -2 because you're going to square it, so it's going to be positive for your b. This gives me, over here I'm going to have 6 times -1, so that's -6, plus 8 is 2. The 4i and the 12i make 16i. And then in the denominator, that's going to be 16 plus 4, which is 20. And we're so close. But what you see is not yet in standard form. And we all made an agreement as mathematicians that we would keep it in standard form. So we want it to be a plus bi separately. So you got to do, what is 2 divided by 20? 1/10. What is 16 divided by 20? Both divide by 4.
4/5.
4/5 I. So I can see my real part is 1/10. My imaginary coefficient is 4/5. Okay, but they're separate. This is an equal sign, not a negative. Okay. So complex numbers are going to be included on your quiz tomorrow. Definitely practice those divisions on the homework and check your answers in the back of the book for the odd problems. That way you know you're doing it right.
4 5.